All right. Afternoon, everyone. Let's continue our course on quantum computing and the introduction to quantum mechanics, right? And let me start with a brief recap of what we've done so far. So let me go through quickly all these postulates of quantum mechanics, right? Postulates of quantum mechanics. So the first one was that quantum state of a quantum system is represented by a vector, right, in a complex Hilbert space, and that the superposition principle holds, meaning that we can represent any state in this space as a superposition over any linearly independent basis, like for example here, right? Then the postulate number 2 tell us that the coefficients of this superposition of this representation, they give us the probability amplitudes of finding the system in a particular state. Right. For example, for a TLS two-level system, we have this, for example, this representation of a state, general state of a two-level system as a superposition of two states, 0 and 1, and this superposition gets this C sub 0 and C sub 1 coefficients, and these coefficients describe the probability amplitude of finding this two-level system in either state 0 or state 1. Right. Then the postulate number 3 tell us that in order to describe a quantum system, we need to basically take classical quantities and assign them a set of quantum operators, like position gets the position operator, momentum gets momentum operator, energy operator, and etc. And these operators are Hermitian by definition, and the Hermitian operators, they have real valued eigenvalues and eigenstates that form the linearly independent basis that you can use to describe your the state of quantum system. So basically, you can use any representation, any basis that belongs to the Hermitian operator to describe your system. And usually we work in either energy representation or coordinate representation or something like that. Then the next postulate number 4 tell us about projective measurements. So basically, before we do measurement, we prepare the quantum system, and we have to assume that, we have to think of the quantum system as it in the all possible states, right? All possible states simultaneously. And then when we do the measurement of a system in some particular basis, for example, we can have a system and do the measurement in the coordinate basis, right? We basically measure a coordinate of a particle. Then as a result of this measurement, we will get the position of the particle. We can do the measurement in the momentum basis. Then we will get the result in the momentum space. We can measure the energy of the system, and then we will get the result in the energy space. And after this measurement, the state of the system collapses to the basically to the result that we detected in result of our measurement. For example, if we have a particle, we measure the particle in the coordinate space. We detect the coordinate of it, and for the same particle, we can measure the energy of the particle, and as a result, the particle will collapse, or the state of the particle will collapse to the particular energy state, etc. Then we also discuss this postulate number 5 that tell us about the time evaluation of the time evolution of the quantum system. So basically, the quantum evolution of a system is described by this Schrödinger equation. This is the main equation in the quantum theory, presented by this one, right? I h bar, then the time derivative of vector state, and it's equal to this operator product of the Hamiltonian and vector state. So we see that the Hamiltonian operator, which is the operator of energy operator, plays the vital role in all this theory. Basically, when we describe a quantum system, we first come up with, construct, or think of some operator, the Hamiltonian operator of the system, or try to guess it, and then basically do the simulation by calculating or numerically calculating this Schrödinger equation. What text? Yeah, the postulate number 6 tells us about time evolution operator and the Heisenberg picture. So basically, we say that the same system, instead of Schrödinger equation, we can use this time evolution operator U, which tell us basically how the system evolves from the momentum t0 to another momentum t, where t is larger than t0. So basically t is the future and t0 is the past. And so basically, if you have a system described by the state vector psi, then what you do, you just apply this time evolution operator to this psi vector, and you get a new psi vector in the later moment of time. Then we have shown that this time evolution operator description is completely fair, and it's basically the same as or nothing but description by the Schrödinger equation. So basically, from the time evolution operator, you can derive this Schrödinger equation, assuming that the time difference between t and t0 is very small. Then, using this time evolution operator, we say that we can write we can derive any operator in the Heisenberg picture, right? So in the Schrödinger picture, the operators don't depend on time, and but using this similarity transformation through the time evolution operator, we can derive this new operator, which is dependent on time, and this is so-called Heisenberg picture operator. So these operators in Heisenberg picture, they do depend on time, and since this operator U is unitary, these two representations are completely the same. They give the same result. So it's just a matter of convenience, which picture you shall use, either Schrödinger equation or Heisenberg equation, Schrödinger picture or Heisenberg picture. The result of your simulation or calculation will be exactly the same, but using that or another picture will or could simplify your calculations significantly. Accordingly, in this Heisenberg picture, we have this Heisenberg equation that describes how the operators depend in time, in contrast to Schrödinger picture, where we have a differential equation for the vector state. In the Heisenberg picture, we have this equation that describes the dependence of the operator. And in some sense, this is actually more like natural, because as we also discussed last time probably, or I mean in the past, that this vector state, this psi vector, is nothing but mathematical construction, mathematical object that doesn't have any realistic it doesn't exist in reality, right? So no psi state or psi vector or wave function exist in reality, in nature. So this approach is kind of artificial. This Heisenberg equation is more intuitive, I would say, because any operator, like here we have this A operator, but instead of like A, we could have operator of energy, operator of momentum, angular momentum, etc. So basically what you do, you replace the classical thing by the quantum operator and get the equation for the operator itself rather than psi vector. And then we probably the last one, right? And the last the last one we discussed so far is this uncertainty relation. So the uncertainty relation, as we derive this in the general case, it tells us that the product of two uncertainties in two quantities, quantity A and B, is always, I mean, larger or equal to 1 over 2i, and then this expectation of the commutator of two operators. So from here we conclude that if the operators don't commute, and the commutator is not equal to 0, like in the case of coordinate and momentum, then this product is it gives you some value, right? And this product of these two, delta A and delta B, is always larger than some value, and that means that you basically cannot think of or come up with a experiment that will allow you to measure these two quantities simultaneously in one experiment with like with high accuracy, right? So for example, this one, like very well known result, delta x delta px is larger than h bar over 2, tells us that we cannot measure the coordinate and momentum simultaneously with accuracy better than h bar over 2. But in this case, I want to make a note or aside. And tell you about so-called squid states. Right, so let me make this note here. So squid state states squid states. So let's write down this general uncertainty relation to I, and then expectation of the commutator of two operators. Right? Yeah. So these two operators A and B, these quantities can be like any, and the fact that we cannot measure, for example, this quantity A with 100% accuracy means that if we represent this quantity on a complex plane, right? Let it be, for example, the real value of the quantity A, and this would be imaginary value of this quantity A. Then the actual value of this quantity A in classical physics is represented by a dot or radius vector like this, right? But in quantum mechanics, since we cannot measure this quantity with 100% accuracy, this quantity gets some area like this around, with the width of this area to be equal to delta A. So this is basically dispersion of the of this quantity A. And for the B, we have like a picture like this also. So now it's an important point to notice that this uncertainty principle and uncertainty relation implies the limit of the product of two, right? Like delta A, delta B must be equal to, must be larger than some quantity C. But we can get this delta A from here. So it would be C over delta B, right? And we see that when we make delta B very small, our delta A will be very large, and vice versa. When we make delta A smaller, delta B becomes larger. That means that we actually can in experiment we can squeeze this state, for example, this state A, this is state A, and now instead of this this spot, this circular spot around it, I draw something like, I don't know, something like this. So now this width is narrower than in the previous one. So now this delta A, delta A, let's put it prime, is less than delta A in the first place. But how we can achieve this? Well, with the increasing in delta B. So I can reduce delta A by the price of increasing delta B, and vice versa. So this is called Squid States. Squid state. Probably we will talk about this more in what follows. All right. So now we can go ahead. Do you have any questions?
No, Professor.
Very good. So now we can go to the postulate number 8. Postulate number 8. the density operator. Density operator. So what is this about? So we say that the system in so-called pure state, described by only one psi vector, can be represented as a superposition of its eigen state, plus etc. So we call this a pure state. Pure state means that we know everything about the system to describe it like perfectly. Yeah, so we know like everything about the system to describe the system perfectly, but however, the description by just one psi vector is impossible in a number of cases. So basically, there is a large class of systems that you cannot describe by just one psi vector. And yeah, so let's consider systems that are not described by single psi vector. So for example, I mean the first one as an example, I bring this ensemble of quantum systems. Ensemble quantum systems. Ensemble of quantum systems. So let's suppose we have a quantum system, and this quantum system is in the pure state psi1. But in this ensemble we have other systems, right? I mean, you can imagine some sort of a gas of quantum systems, and each of these subsystems is in the pure state, like this one is psi 2, this one psi 3. Another one could be again in psi 1, this one psi 2, etc. And but the problem is that we don't know, I mean, the number of these systems, these quantum systems in the ensemble is so large that we cannot uh, keep track of all these subsystems. Like in a gas, we cannot keep track of all the single molecules in the gas. What we can talk about only the probabilities, probability of finding a particular subsystem in a particular state. For example, for a arbitrary state psi I, we can we can define this probability pi, right? And since this is the probability, it obeys this normalization rule. So uh, some of these uh, probabilities, all of them is equal to 1. Right. So this probability, now this pi, uh, appears because of the lack of our knowledge about the system. In contrast to this ci modulus square, which is also probability, the quantum probability. This is something like, I mean, this is how the nature works. This is because of the quantum properties of matter, of our quantum system. And we cannot get rid of this anyhow. But this one, this pi, is just because we don't like know enough about the system under consideration. We cannot predict with 100% certainty what which subsystem we will observe. We can only predict them, and these two probabilities are different. Example would be like a for example, electron gun, right? Some this is a system with some like heated metal inside, and this gun provides us electrons with some velocities, right? Vi. And since this is the thermal process, this element here has some temperature T, or energy T, the Boltzmann constant times this temperature. So we cannot predict what exactly the velocity of this electron will be. What we can do, we can use this Maxwell-Boltzmann distribution of these electrons over the velocities, over the possible velocity, something like this, right? With the expected velocity v and the average velocity v here, and this is the distribution rho. And in this case, in this experiment, this p would be something like the product of rho times dv. So this is the first example of systems where we cannot use only psi state and this quantum probability. We also need to bring this classical probability, let's say this way, classical probability, the ensemble of quantum systems. Another another important problems where we cannot use only psi vector to describe the system is a system consisting of two parts, of two interacting subsystems, like subsystem A, subsystem B. Of course, the system can be described as a system, as a wall, but at the same time, if we concern only about the state of a subsystem A, we cannot write the psi vector of the this subsystem A because well this state depends on the subsystem B because of their interaction. Right. and the last one, maybe even more important, is that any system, like in reality, any system is actually open, meaning that it interacts with external space. For example, if you have a quantum system like this, then this quantum system interacts with vacuum, interacts with like surrounding maybe gases, air, if it's not a vacuum, etc. So this is so-called open system. Open system. So these three examples tells us that the description by the psi vector in general case is not sufficient, and we need to come up with a like a more advanced approach to this quantum description. And this approach is called density operator. Density operator. So how we introduce density operator? Let's consider a expectation expectation value of operator A. What it is? It is the matrix element like this one, right? This psi state, then this operator A, and then the same the same psi state. So basically, this is the expectation value, the value that we most likely observe in the experiment. Or, well, actually, after doing the experiment many times. So this is the average value of the average value of the quantity. So now, instead of just one psi, we have like in this example, psi 1, psi 2, and other states in this ensemble of quantum systems, right? We have a set of we have a set of pure states, with certain probabilities p1, p2, p3, etc. So the natural way to generalize this this expectation value, well, expectation value is something that we measure in lab. That's why we need to start from expectation value, right? Because and do some mathematical operations that keep expectation value unchanged. Keep the expectation value unchanged. So the natural way to generalize this would be to take a sum of these matrix elements I, A, psi I, right? The matrix elements for each of these pure states in our ensemble, and of course multiplied by the probability of finding this particular of each state, state I, right? So let me write this down here. So this is a sum of over I, pi, and then psi I, a operator, psi I. Yeah, the sum like this. If you have just, if you have the pure state, pure system, a system that can be described by just one psi vector, then in pure state, in pure, we have only one probability of finding just one, right, of one particular state. So this P would be equal to 1 because no other systems, subsystems in our ensemble. And then this turns back to this definition of the expectation value. But in this case, in the case of the ensemble, we have to average all the states over these classical probabilities PIs. So now let's rewrite this a little. So we can we can take this bra vector and write this on this right side, right, like this. So it will be pi, then this operator a, then psi I, and then this psi e, like this. And now, since these pi's are just constants, right, we can exchange the position of pi and the operator a. So I will get the following. Operator a, the sum, and then pi, the psi I, like this. So now I see that this is something, this is another, I mean, I can denote this by another operator. Let's denote it by operator rho. And this is called the density operator. Density operator. So the expectation value of any operator would be equal to the sum over this operator A and operator rho. I mean, their product. That means that we have to take the sum over their product, which is equal to the trace of the operator A and operator rho. The trace. So let's write this again because this is quite important formula. So the expectation value of any quantity can be found by taking the trace of the operator A of this operator with density matrix. And the density matrix by itself is nothing but the sum over these classical probabilities times this projection operator psi I. So let's frame these two formulas. The second one is the definition of the density operator, and the first one is the main formula in this story, because this formula allows you to calculate the expectation value of any operator for a known density matrix. So let's consider a few properties of density matrix. Do you have any questions by now?
No, Professor.
Very good. So the properties of density operator. So the first very important one is that density operator is actually a Hermitian. Hermitian operator, meaning that it's Hermitian conjugated coincide with itself, right? I mean, it's very easy to see that because, well, these PIs, these classical probabilities are real numbers, right? And then what we need to check that this operator Psi is Hermitian. Well, is Hermitian, so we take the dagger, the Hermitian operation. I remind you that taking the dagger of two operators A and B gives you operator B times operator A dagger, B dagger times A dagger, right? So it will be psi I dagger and then psi I dagger, and taking the Hermitian conjugation, you have to transpose and make the complex conjugation. That means that the first one will become cat vector, and the second one will be the bra vector. So it didn't change, of course, because this is the projection operator, as we discussed last week. So this is the Hermitian operator. So the next property is that trace of the density operator is always equal to 1. Let's check that. So trace of operator rho is nothing but, I mean, let me write this rho operator here. So it is a sum of some I, then psi I, like this, right? So now let's find this trace of this operator. Finding the trace of the operator means that we have to transform this operator in the matrix representation. So let me write this step by step. So to transform any operator to the matrix representation, I have to multiply from left and right by the states, right? For example, psi m on this side and psi n on this side. So this will be the matrix elements n m like this. And now I have to take the trace of this row nm, which means the sum over row nn, right? I have to take the diagonal elements and sum them up. So let's return to my definition for the density operator. This is the sum over pi and then psi I. And now I have to I have to multiply this by psi j on, I mean j or any letter on the right and on the left. On the left also psi j. The same index because I'm finding the elements, I mean the diagonal elements. So it will be trace of a row like this. And of course another sum. So one sum runs over I, another one runs over j. Right, so it's equal to of course I can, of course this summation over j must be written here, because yeah, like this. So this pi is just the constant, right? So the same I can rewrite in this form, this summation over I, this summation over j, and then pi I put in this first place, and then here I have two inner products, psi j, psi I, then psi I, this one, and psi j. Okay, so we can recognize these two delta delta matrices, ij, this also delta ij. So all this is simplified down to just the sum over I pi. I hope this is already clear to you, why this summation over something is multiplied by this delta Kronecker tensor, this matrix, gives you in this case pi, and this summation, the sum over all pi's gives you 1, because this is the probability of finding the particle or the system in any state. So the trace of the density operator is always equal to 1 because of the definition of the probability. Very good. Do you have any questions regarding this? So then next, there is another property that says us that for a pure state we have rho squared equals to rho. It's very easy to show, because rho is equal to the sum of pi psi I psi I, and when I take the square, right, I have to take the square of this. It is nothing but two sums I and j, and then I have this pi pj. Mm, let me see, let me see. Oh, no. I'm wrong. For the pure state, so it works only for the pure state. In the pure state, I have only one possible psi vector. So my rho in pure state is equal to this psi times psi operator. Right. My all piece, the probabilities all equal to 0, but just one. 100% of probability of finding system in the particular state, in the particular pure state. And yeah, and now if I take the square of this, what I will get this psi, and then times this construction again, which is nothing but psi. Right. So this, because this psi state is the orthonormal state, right? So this is 1. And we conclude that this is equal to psi times psi or rho. So but for the pure state, so the square of the pure state gives you, is equal to just the square of the density operator in the pure state is equal to density operator of the pure state. Yeah, and fourth, this is what we already derived. This expectation value of any operator is simply the trace of this operator with the density matrix. Well, now let's make a side regarding the physical meaning of these elements of the density matrix. So we know that we can represent the psi state as a sum of the as a superposition of the possible eigenvectors, right? Eigenvectors of a operator. So it will be Ci, and let's denote these eigenstates by Ui's. Something like this. So in this case, this density operator in the pure state is equal to psi, right? And by the way, this from here we conclude that the bra vector is equal to the same, but this C complex conjugated. Well, I have to write U first, I, and C I complex conjugated, right? So let's take this, let's rewrite this using these two formulas. Plug in this two to this one. What we get? We get this sum. This is I, this is I. So it will be sum over I. Then this bra vector I, then C I. No, completely wrong. I have to first start with this one. So it will be CI UI, and then U J C J. I have to use another index because I J, right? To another index because I is taken already, and this is the product of two, so the index here must be different. C J complex conjugated. Okay, and now I notice that I have to I can rewrite this one. Basically, so this is the product, this product of two, and I can rewrite the same in two terms. The first one will be the product of the same projections of the same components. So it will be C I modulus square, and then here it will be UI like this, and the summation will run over I, and then plus the rest, the extra terms when I is not equal to J. Right, in this case it will be CI complex conjugated, state I, state J, state J. Something like this. So we remember that these quantities, this modulus Ci modulus square, right? It is nothing but probabilities, and they are real values, and they are the probabilities of finding the system in a particular state. In this case, is state I. So this is a real values that describe a probability of finding the system in a particular state. But on the other hand, we have also these terms here. With these coefficients, Ci, Cj complex conjugation. And they are, of course, complex. Well, by definition, the projection in the Hilbert space, the projections of vectors is a complex number. And the product of two complex numbers in general case is another complex number. So this complex, and we can actually find the amplitude and the phase of these terms. So for example, for the Ci, we can represent Ci as a modulus Ci, right? This is the length of the complex number times e to the power of I, some phase phi I. So this length of the complex number and the phase of the complex number. And the same for the Cj, right? For the Cj complex conjugation, we will get Cj, then e to the power of minus I phi j. So the product like this, Ci Cj complex conjugation, will be the modulus Ci, then modulus Cj times e to the power of I phi I minus phi j. Right. So these coefficients now, these elements, let's call them off-diagonal elements, right? They are off-diagonal elements. Off-diagonal elements. Well, they describe the the quantum phase, right? The quantum coherence of different states because of this phase term. Because of this term, phase term, these elements, these off-diagonal elements, they describe the coherence of quantum systems, the coherence, the off-diagonal elements describe the the coherence, the quantum coherence. Let's call this quantum coherence, or well, the ability of quantum system to interfere, or quantum state to interfere. The ability of a quantum state to interfere. So the diagonal elements of density matrix, they describe these probabilities of finding system in a corresponding state. The off-diagonal elements, they describe the coherence of the all mutual states. And the coherence here means that if the system, for example, is in the state 1, this state affects the probabilities of finding the system in the state 2, etc. And for example, for the two-level system, let's write this down. For the level system, what you'll get. In this case, it will be rho. This is, by the way, again, this is a pure state, still pure state. And the diagonal elements will be the probabilities of finding the two-level system in the first state and in the second state, 0 and 1. And these two will be the off-diagonal elements, will be C1, C0, C1 complex conjugation, C1, C0 complex conjugation. All right. So diagonal elements give you the probability of finding the system in the particular state. I remind you that our two-level system, a system like this. This is the 0 state, this is the 1 state, and these are different energies, for example. And C sub 0 gives you the probability of finding the system here. C sub 1 gives you the probability of finding the system in the state 1. And the off-diagonal elements, they give you the some sort of quantum interference between the states when one state affects the another one. So when they are not equal to 0, then the fact that the system is in the state 1 affects the probability of finding it in the state 0 and vice versa. This is how it works. So this is so-called quantum interference. Interference of, in this case, this is interference of states.
Excuse me, Dr. Alex.
Yes.
Can you explain me the above equation? Just few lines above you wrote an equation. Yeah, just that in the red one, the summation equation. I didn't understand how that came. The last summation equation.
Yeah, maybe I wrote this a little bit wrong. So what I did here, I I took this superposition, right, and plug into this formula on the left, and then I get this one and plug in this one on the right, and summation must be different. So this is might be confused you. So you have this summation over I, then another summation over j, u j, and c sub cj complex conjugation. Yeah, and then you take the the product of two, right? When, I mean, for example, when you have two factors like this, like a1 plus b1 multiplied by a2 plus b2, right? What you will get? You will get a1 times a2. Then you can write plus b1 plus b2, right? This is basically the product of this and this, this and this, and then plus the this remaining parts, a1 b1 plus a2 b2. So these terms these terms let me see.
I think it should be A1 B2 and A2 B1. The third and fourth terms.
Yes, yes, yeah, exactly. A1 B2 and A2 B1. Yeah, exactly. So you see that I mean, it's correct, but for the following, what I maybe let me see. Maybe instead of let's maybe rewrite this way. So instead of this, let's write a1 plus a2 times b1 plus b2. So I will get a1 b1 plus a2 b2 plus a2 b1 plus a1 b2. Right? So now here I put on the first place the terms with the same term, with the same indices, a1 b1, a2 b2. So I can rewrite this the same way as ai bi, right? Like this. This is exactly the same. And then plus these remaining coefficients here, these remaining terms, which indices are different. So I write this I doesn't equal to j, and it's equal to a I b j. The indices are different, so I put just on the first place the terms with the same indices, and then the second term all the terms with different indices. So this is exactly what I did here. The first term with the same indices, so you will get here ci complex conjugation, which gives you Ci modulus square. And the second one, the indices, the terms with different indices. So it will give you Ci, Cj, complex conjugation. Is this clear now?
Yes.
Okay. So let me, I guess I can remove this part. All right. So, but do you understand this? Do you understand this matrix and what the matrix, the density matrix element describe?
Yes, it's clear.
Very good. Yeah. So, I mean, as you can see, it's very, very interesting construction in interesting matrix. The diagonal elements describe the the probability of finding the system in a particular state. We call this population probability, right? The population of each state. And the off-diagonal elements, they describe the quantum coherence. They describe the quantum coherence. Well, and this is for the pure state. No dissipation, no other systems, no interaction with the external systems, just a quantum system like, well, I mean, as it is. But due to the interaction with externals, etc., well, in the completely, I mean, we can get completely mixed state. In the completely mixed state, we can rewrite this in the mixed state. In the mixed state, we don't have this off-diagonal elements, right? And so we will get something like this: C sub 0 square, then 0 here, and C sub 1 squared. Okay, let's make a brief break, and I will get back in maybe 10 minutes, okay? Let's have a break. Okay, I'm back. Yeah, where I were. Yeah, so in the mixed state, due to the interaction of the system with external BAF, with other systems, etc., the quantum system loses its quantum coherence, and in the ultimate state, right, of no quantum coherence, these off-diagonal elements will be equal to 0, and but of course with some probability amplitude of finding the system either in either state 0 or state 1. Okay, so now let's consider an example. So what is the density matrix of a quantum system in the of a two-level system with in the state of quantum superposition? What is the density matrix of two-level system in in quantum superposition? Superposition is psi is equal to 1 over 2, right? And two states 0 plus 1. So the equal probability of finding the system in either state 0 or 1. Equal probability. So this is the superposition state. What is the density matrix? So it's very simple. This is the poor state. So the density matrix is just the outer product of these two vectors, right? And it's equal to 1 over square root of 2 now, because I have this prefactor twice. And then what I get this state 0 plus state 1, and it's multiplied by state 0 plus state 1. Something like this. So it is equal to 1/2, and then I have 4 terms. State 0, 0, then plus state 0, 1, plus state 1, 0, plus state 1, 1, right? Or in the form of matrix, we can rewrite this in form of matrix as 1/2, and then this is the elements, right? So this coefficient 1, 1, 1, 1. So the matrix is 1, 1, 1, 1. Yeah, this is the density matrix of the two-level system in the state of superposition. The state of superposition. And in the state of superposition, this TLS. And and of course the same. I mean, for the same system in the poor mixed state, I just need to turn to 0 the off diagonal elements. So the matrix will be 1, 0, 0, 1. Or in the outer product representation, it will be 1 over half, and then state 0, 0 plus state 1, 1. So this is the complete mixed case. What happened to my sorry, my tablet gone crazy. Yeah. So the poor state of the TLS system, the density operator of the TLS system in the poor state and the mixed state. And in the general case, right, this general TLS, this is poor, will be what? It will be C sub 0 modulus square. Oh, we already wrote this above, but let me just repeat it here. C0 and C1 modulus square. Okay. So what about the evolution of density matrix? Let me change the color. The evolution of density matrix, right? So we have Schrödinger picture, Schrödinger equation, Heisenberg picture, Heisenberg equation. So for the density matrix is another way to represent quantum mechanics, and of course density matrix gets its own evolution differential equation. And this is important because this differential equation, which is named after the scientist von Neumann. It's a von Neumann equation. So the von Neumann equation is more like is very popular now because it allows generalization to like any quantum system whatsoever. So I guess it's important to say a few words about this von Neumann equation, especially because it is pretty easy to derive this one. So to derive this von Neumann equation, we start with the definition of the density matrix, density operator, right? And we derive this take the derivative of this density operator by time, and the probabilities don't depend on time. I mean, in general they do, but let's consider the case when the steady state, right, when the probabilities don't depend of time. Otherwise, this is the case of kinetics. It's another subject. Right. So the derivative, time derivative of this one will be the derivative of the first times second, and then plus first times the time derivative of seconds. Something like this. So at this time, I recall the main equation, Schrödinger equation, right? This psi I over t is equal to Hermitian operator psi I. So from here I can get the formula for the derivative. So it will be 1 over I h bar Hamiltonian psi I. And well, this is for the cat, right? And for the bra, I can write the same. I just need to take the complex conjugation, so it will be -1 here. And then I have to flip these two guys, and well, and the Hamiltonian is the Hermitian operator, so the Hermitian conjugation is equal to the operator itself. So I get these two, and now I plug in these two to this equation above. So what I get? I get d rho over dt is equal to the sum over I pi. Then I have this 1 over I h bar Hamiltonian psi I and here psi I and then minus the sum of I pi 1 over I h bar psi I, then psi I Hamiltonian. Is this clear?
Yes, Professor.
Yeah, Professor.
Very good. So Now I notice that I have these common terms here and here, right? I can take them out from the brackets and I'll write the same this way. So it will be sum over I. Let's take it out actually. I h bar, then sum over I, then pi. Let's now exchange this deposition of pi and h because pi is just constant, so I can exchange the position, right? So it will be a Hamiltonian, then pi, and this psi I, and then minus. And here I leave it like this: pi, psi I, Hamiltonian. So now I see that this this guy here, right, the sum over pi and this outer product is nothing but the density operator here and here. So it is equal to 1 over I h bar, and then this Hamiltonian times rho minus rho times Hamiltonian. So this is the commutator h rho, and this guy I can rewrite as minus I over h bar to make it consistent with the literature. So the result is minus I over h bar, and then commutator of the Hamiltonian with the density operator. So the resulting equation is delta rho over delta t is equal to minus I over h bar commutator of Hamiltonian and the density operator. And this is the very well known von Neumann equation. Von Neumann equation. Very important one for quantum theory. Well, not only as a like equation itself, but maybe the generalization of this equation to so-called open quantum systems when we add the like any interactions of the quantum system with any external objects, with the temperature, with the buff, etc., etc., just by adding some terms on the right side. So yeah, von Neumann equation. And of course, when you for a given Hamiltonian, you can solve this equation, find the result, basically the density operator as a function of time, and then as you get this result, you can find the actual expectation value, right, as simply just a trace of the density operator with the operator A, with the operator of the quantity. So these two equations is basically the solution to any quantum closed quantum systems, let's say this way. And about dissipations we will talk about just a little later. Okay, so let's consider example now. Example. And as an example, let's take the simple two-level system. Two-level system dynamics. Two-level system dynamics. So let's consider a two-level system, something that we call a qubit, right? Without any interactions, without any dissipations, just the qubit as it is. Like a perfect quantum system that, by the way, never exist. But we build our story step by step. So let's consider this simplest case now. I mean, it's dynamics. So the qubit consists of two levels, level 0, level 1. The level 1 is excited state, and the ground state 0 gets the energy E0, the excited state gets the energy E1, and we have some sort of like electron or oscillator that can transit between the ground state and excited state. When my red dot in the ground state, my system, my qubit is in the lowest energy state. When I excite it, or in general case, it can jump up to the excited state, and then I say that, oh, my qubit is in excited state. So to use this von Neumann equation, we need to start with the Hamiltonian. So let's come up with the simple Hamiltonian of this simple system. And we already discussed that the Hamiltonian of the system in the energy energy representation is just the matrix of the energy of the ground state, then 0 here, 0 here, and then energy of the excited state, right? something like this. At this moment, I also want to bring this formula that connects the energy with the so-called angular frequency, right? So sometimes we write this energy of a state as just the product of h bar, the Planck's constant, times this angular frequency. Like for a photon, sometimes we describe a photon in terms of energy, sometimes in terms of frequency. So the energy and frequency connected through this Planck's constant. This works always. So this connection between energy and frequency is just definition of angular frequency. Nothing but that. So the same I can rewrite as the product of this h bar, and here omega 0, which is the angular frequency of the 0 state, then 0 here, 0 here, and omega 1. Right. So this is the Hamiltonian. The next step, we need to calculate the density matrix. So let's write this density matrix of a two-level system in the general case of a pure quantum system. It is C sub 0, right, squared. Here then C0, C1 complex conjugation, then C1, C0 complex conjugation, and C1 modulus squared. Okay, So now let's write down this one Neyman equation once again. So it is simply minus I over H bar, then a Hamiltonian, and rho the commutator. So well, we have two matrices. Let's calculate first the product of the Hamiltonian and density matrix. So it will be what? It will be H bar, then omega 0, 0, 0, omega 1, the first matrix, and the second one. I don't want to write the C0, etc., C1 modulus. I just write this by components: rho 0, 0, rho 0, 1, rho 1, 0, rho 1, 1. Right? And for example, rho 0, 0 is 0 module squared, etc. So the matrix product of these two gives me what? It gives me H bar, and then another matrix 2 by 2. I multiply omega 0 by rho 0, 0. So I get omega 0, rho 0, 0. Then 0 by rho 0, 1. So it's 0. And then for the second one, omega 0, rho 0, 1. And then here I get omega 1, rho 1, 0. And omega 1, rho 1, 1. Is that correct? Yes. Okay, and for the commutator, I need another product of rho by H. So it is H bar, and then rho 0, 0, rho 0, 1, rho 1, 0, rho 1, 1. Matrix product with omega 0, 0, 0, omega 1. It will give me the another matrix 2 by 2. And here I get what? It will be omega 0, rho 0, 0. Then omega 1, rho 0, 1. Then omega 0, rho 1, 0. And finally omega 1, rho 1, 1. Correct? Yes. So now the commutator of H rho, which is nothing but H rho minus rho H, is equal to the subtraction of these two matrices. So it give me H bar for sure. And then here, well, I noticed that the diagonal elements here, here, and here, they are the same. So the subtraction gives me 0 for the diagonal elements, 0, 0, 0 here. And for the off-diagonal elements, I can take the matrix, the density matrix elements, factorize it, and here we'll get omega 0 minus omega 1. And here, rho 1, 0, omega 1 minus omega 0. Something like this. Right. So this von Neumann equation by components, if I rewrite this by components, it will be delta rho mn, right, E over h, and here the commutator h rho mn. I can write this in matrix form like this. So here I conclude that, for example, for the component 0, 0, I will get d rho over dt 0, 0 it gives me 0 for this component. So the rho 0, 0 is a constant. It doesn't change in time, so the time derivative is equal to 0, so rho 0, 0 is constant. And I remind you that rho 0, 0 is actually the modulus of C0 squared, which is the probability of finding the system in a state 0. The same for the second one, 0 d rho 1 1 dt is equal to 0. So rho 1 1 is also constant. It's another constant because the rho 1 1 is C1 modulus squared. It's another constant. It doesn't depend on time. And this is actually interesting. We will discuss this in a minute. And and for the off diagonal elements, I'll get d rho 0 1 over dt, and I get this coefficient here. I will get h bar, then omega 0 minus omega 1, and rho 0 1. This is differential equation, can be easily integrated, right? So the solution is rho 0 1 is some constant times e to the power of I've lost something. Yeah, I've lost this this prefactor here, so it must be multiplied by minus I over h bar. So it will be yes, the h will be which cancel, and I get only minus I, something like this. So the result will be minus I omega 0 minus omega 1 t. Yeah, simple harmonic dependence in time with the frequency of the difference between the states. The larger this difference, the larger the frequency of oscillation. The lower the difference, the lower the frequency. And for the the same way for the rho 1 0, it will be another constant, of course, but this function will be the same, but up to exchange of these frequencies, omega 1 minus omega 0 t, because here it appears with opposite sign. So you see that in this simplest case of two-level system without interaction with any fields and without dissipation, we've got the following result, that if the system is for example in the excited state, in this C1, then this C1 will be equal to 1 and C0 will be equal to 0, right? So this system will be like forever staying in this excited state. If these two equal to 0.5, 0.5, something like this, so it is equal probability of finding the system in either upper state or the ground state. It will always be like this. The system will be always in this state. Of course, this is not the case. In reality, if we excite the system to excited state, it will decay to the ground state, and this decay is due to the interaction of the system with the thermal bath, And this is something that we will discuss soon. But yeah, so this is about the density matrices and its definition and how all this works. So it is a little bit longer than usual than other postulates, but we had to go through all this. And finally, the last one, the postulate number 9. This one is about the composite systems and quantum entanglement. Description of composite systems. And quantum entanglement. Quantum entanglement. So we already mentioned that when we have a composition of two systems, of quantum systems that interact, we can describe the system in the total system in terms of density matrix, of course. But anyway, I mean, something interesting happens when we bring two quantum systems into interaction. And now we're gonna figure out what actually happens when we do so. So let's consider two quantum systems. Consider two quantum systems. The quantum system is described by the psi state, right? And this psi state is like defined in its own Hilbert space. So for the first one, we have psi 1 in Hilbert space, we denoted by V, so it's V1. And for the second system, we denote the state psi 2 in V2. The state psi 2 in the Hilbert space V2. The V1 and V2, it is Hilbert space. Hilbert space of the first or second quantum system. Second quantum system. So how we describe the combined system? How we describe the combined system? How do we describe the combined system? So first of all, let's talk about the space. The new space of the combined system is the tensor product of the first and the second one, the tensor product. This is the definition of tensor product. Whenever you take the tensor product of two, for example, vectors, you get an object of larger dimensions, right? We already discussed that if you take the outer product of two vectors, this is another example of tensor product, you get a matrix or tensor. And of course, these objects of higher dimensions, they have to be, they belong to the space of higher dimension. That's why we have to, like, that's why the product of two spaces is a new space, and this operation is tensor product, and the result is a new space V. And so let's suppose that the dimension of the first one, the first space, was P, and dimension of the second one was Q. Then the dimension of the combined system, combined space, will be, guess what, P times Q. In our case, the most important one, I mean, for us, the most important case is two-level system. So this is the Hilbert space of 2, then P and Q is equal to, and the resulting space will be 4. So the combination of two-level systems, two-level systems, two TLS, is another quantum system with the in the Hilbert space of 4, of dimension of 4. The same way, the same way for the state vector, we have to take the tensor product of the first and the second one. And as a result, we'll get this new psi vector. And yeah, this is the way how we define this psi vector of the combined system. Combined system. And again, if psi 1 and psi 2 are vectors of two dimension with two elements, then the combined psi will be the vector of 4 elements. And finally, if, for example, operator A acts on psi 1 in space 1, and another operator B acts on the state of the second system, and it's defined in the space V2. Then we can define the operator, which is the tensor product of two operators, and it acts on the combined system psi in the combined state V. And the rule here is that the operator A is still acts on the vectors psi 1, and the operator B acts on the vectors psi 2. For example, for this operator, if it acts on the so by the way, there is another method to write this tensor product of two vectors. So here we wrote that this tensor product is equal to, like, I write it like this: psi vector 1 tensor product psi vector 2. This is the same as and we will very often use this notation. This is just the psi1 times psi2. Or this is the same as just one single vector with psi1, psi2, something like this. So this is completely the same. If you keep track of what is psi1, psi2, you can write even like in this form, the product of two vectors. So let's get back to this tensor product of two operators, and let's suppose it acts on this psi1 vector, psi2. So this composed vector state. So the rule here is that this A still acts on the first and B acts on the second. So it will be operator A psi1, then operator B psi2. Okay, so let's consider matrix representation, and it will be, I guess, clear what I talking about here. So let's consider two operators A with elements A11, A12, A21, A22, and operator B with components B11, B12, B21, B22. All right. So well, the tensor product of one tensor and another tensor will be nothing but the matrix of, so what you do basically, you multiply this matrix B by all, well, you multiply the elements, all elements of the matrix A by the total matrix B. So it will be, for example, A11 multiplied by this matrix B, then A12 multiplied by matrix B, then A21 multiplied by B, A22 multiplied by B. So now this is the matrix of 4 submatrices, right? So I can divide it like this. So each element in this matrix is another matrix 2 by 2. So let's find this. So what I do, I take the first element A11 and then B, which is B1, 1, B1, 2. So it gives me this matrix A11, B11, then A11 again, B12, then A11, B21, then A11, B22. This is the first submatrix, right? And then second one, A12, B11, A12, B12, A12, B21, A12, B22, and here A21, B11, A21, B12, A21, B21, A21, B22, and finally A22, B11, A22, B12, A22, B21, A22, B22. Okay, so yeah, as you can see, for example, this element, this is nothing but A21 times the matrix B. That's it. And the result is the matrix 4 by 4. Matrix 4 by 4, as we could expect, because in the space of 4 dimensions, the matrices are 4-dimensional, right? So the they're they are all 4x4, supposed to be 4x4. The same way, the product of two vectors, for example, vector A and tensor vector B, this is the same as vector A, vector B, vector B, right? Again, this matrix product rule works. For example, these are two ket vectors, right? So I can write this as A1, A2. This is first ket vector, which is the column, and then tensor product of by the second one, B1, B2. Again, this is nothing but the first element of the first vector times the vector B, and then the second element times the vector B, or it is the following four-dimensional vector A1, B1, A1, B2, A2, B1, A2, B2. Okay. So now let's consider is it clear?
Yes, Professor.
Very good. So now let's consider example 1. Example 1. So suppose I have a superposition state psi, which is 1 over square root of 2 state 0 plus state 1, right? We already know this. So the problem is to find the power of this state by, for example, 2. So I can write this as a power of like this, tensor product 2. So so first let's rewrite this state in the matrix form. We already did this, so it's supposed to be very simple. So 0 state is 1 0, 1 state is 0 1, right? So the result is 1 over square root of 2, 1 over square root of 2, the vector. Okay, and now this tensor power of the vector by itself is nothing but the product of vector by itself, like this, right? If it would be free, it would be free vectors here. So and now it's equal to what? It's equal to 1 over square root of 2, 1 over square root of 2, tensor product 1 over square root of 2, 1 over square root of 2, and again I just multiply each element by the matrix, so the result will be 1 half, 1 half, 1 half, 1 half. The vector of 4, and all the elements are 1 half, or 1 half and the vector 1, 1, 1, 1. Something like this. And more interesting example 2, and let's call this entanglement. So we're gonna talk much more about the quantum entanglement. Here I just want to introduce this concept and like the idea why it like appears in the theory. So so let's consider let's consider two systems, like system A and system B. And for now, we don't have any interaction between two systems. So no interaction. No interaction between them. How to find the psi state of the system without interaction? So it's just a product of corresponding state vectors, right? So the total state will be what? It will be what? It will be the state of the subsystem A, then the product of the system B, right? Or this is the same as like psi A, psi B. You can rewrite it this way. So this is nothing but, so I consider two level system. These are TLS, two level systems. So for the first two level system, I can write the coefficient C1 of subsystem A and the eigenstate psi 1A plus C okay, C2. I mean, before we used these different indices, we denoted the first state 0 and the second 1. Now I denote this first 1 and the second 2. It shouldn't like cause any confusion, I guess. So this is C2. Oh well, I can simply change this notation here to make it consistent. So the C0 psi 0, C1A, C1A, and is multiplied by the second one, C0B, psi 0B plus C1B, psi 1B, right? And now when I expand the brackets, I will get four coefficients with the following: C sub 0 A, C sub 0 B, and then psi sub 0 A, psi sub 0 B, plus C sub 0 A, C sub 0 1 B, psi 0, psi 1, plus C1A, C0 B, psi 1A, psi 0 B, and finally plus C1A, C1B, and state psi 1A, psi 1B. So as you can see, the system of two elements, of two subsystems generates the vector, the superposition, right? The superposition of four vectors with four projections to corresponding basis vectors. This is the first projection, second projection, fourth, third, and fourth. So I can, in this basis, I can write my vector, the resulting vector psi, as a column vector of these elements C0A, C0B, then C0 AC1B, then C1A, C0B, then C1A, C1B, right? So this is completely the same vector written as a column of components. And my basis became for component, right? So it will be like psi I, psi j, a, b. The vectors like this, and the 4 vectors of this. Yeah, but this is about like when we have no interaction. When I have no interaction, I can. What is the difference between no interaction and the system with interaction? So when I have no interaction, I can write the state in this case, in this form, like separable form or separated form, when I have one state of one system, another state of another system, and their product. And in the result, of course, I expand the brackets and got this more like longer expression. But I can I can factorize it back and write as a product of 2 states. So this is a separable state. This is separable state. Separable state because I can separate them as a like factorize them. I can factorize them. I can represent the state as a product of 2 states, of 2 vectors. But when I have interaction, when I allow these 2 systems to interact, instead of this vector, I will get another one with coefficients C00, C01, C10, and C11. So as you can see, the difference is that if here I write these coefficients as a product of 2 and I keep track of which system each component corresponds to. Here I write these coefficients just like one single element. Why? Because the state of 1 depends on the state of the other one, right? You cannot separate them. You have this because of this interaction, because of the interaction one depends on the state of the other one. Another one. That's why you cannot like separate, right? You cannot separate this C sub 0 into the product of 2 C0, C0 because they interact, and the state of first part of the system affects the state of the another part of the system. And and this is already called quantum correlation. I guess it's like useful to write this down. Quantum correlation. Correlation, because if you do something with one part of the system, it immediately affects the state of the other part of the system. For this reason, it's called quantum correlation. The two subsystems basically correlated. But now, what I actually want to notice is the following. So before that, let's introduce these states, which are the tensor product of this 0 and 1 states, this basis two-level system states, right? This 0 state is nothing but 1, 0. The 1 state is the state 0, 1. You remember that. But the same way I can take the product of two. For example, the product of 0, 0, right? I can compose this state, or 0, 1.
Dr. Alex, just a question
Yes?
here.
Yeah.
Yeah, this quantum correlation, this is exactly what coupling means, right? Two systems are coupled.
Yes. Yeah, exactly.
Yeah. Okay.
Yes, and so this correlation, yeah, exactly. So in classical physics, we call this like interaction, coupling, and if you have two like resonators, you put them together. Of course, they exchange the energy and their state, like for example a field. If you're talking about electromagnetic resonators, they interact through electromagnetic wave, and they exchange their fields, so they also correlated. In this sense, this is not like a quantum effect yet, but now I'm going to introduce this entanglement, and this is something like truly quantum. So, and for that, we take the tensor product of state 0 and 1. In this case, we get four states: 0, 0, 0, 1, 1, 0, 1, 1, right? For example, vector 0, 0, what it is? It will be state 1, 0, 0, 0. The state 0, 1, it will be 0, 1, 0, 0. If you take the product of two tensor product of two vectors, like we did here, you will get this result. The state 1, 0, it is 0, 0, 1, 0, and finally state 1, 1, it is nothing but 0, 0, 0, 1. So this is the basis in the new four-dimensional Hilbert space. Four-dimensional Hilbert space that we bring to the story, because we need to describe a system of two-level systems. That's why we need the Hilbert space of 4 dimensions, right? And and now let's suppose, for example, I can in this so when I describe this composition of two-level system, I came to a structure like this, to vector like this, right? With components C0, 0, C0, 1, C1, 0, C1, 1. But what if I can get rid of some of these coefficients? For example, from coefficients C sub 0, 1 and C1, 0. What if I can make them equal to 0? In that case, I will get the state. Let's denote it by omega capital 1. I will get the state like this: 1 over square root of 2, and only two vectors, right? 0, 0 plus vector 1, 1. So I just assume that I can, in my general system, I can get rid of these two coefficients, this one and this one. And I only left with the vectors where C00 and C11 are not equal to 0. For this case, they are actually equal to 1 over square root of 2. So this is so-called Bell state. This is important state, that's why it gets its name after this famous experimentalist and theoretical physicist, Bell's state. Let's also say that this is the first Bell state. The first Bell state. Oops, it's not good. First Bell state. Why first? Because I can come up with another one. Let's denote it's omega 2. It's equal to 1 over square root of 2, and now write something like 0, 1 plus 1, 0. I will tell you in a second why this is so important. So this is second Bell state. And the same way I can come up with another two, like this omega 3. I just change the sign in the brackets. 0, 0 here minus 1, 1. Oops, I'm running out of charge. Let me connect my. Okay. This is the third, and finally the fourth Bell state, which is again 1 over square root of 2. I remind you that 1 over square root of 2 is just normalization, prefactor. Right, and this is the following. This is the 0, 1 minus 1, 0. This is the third, and this is the fourth Bell state. I guess the most important one is the first one, but in general, like all of them are very well known as Bell states. Why they are so important? They're important because you cannot. let's take this combination 0, 0 plus 1, 1. You cannot represent this as a product of two vectors, like vector 0 time plus something like 1 times, for example, vector 0. It will give you state 0, 0 plus state 1, 0, but not 1, 1. So that this is wrong. So you cannot represent this 0, 0 plus 1, 1 state as a product of two vectors of independent systems. And that's why it's called non-separable state. Well, this state like this also non-separable. So this is also non-separable. It's non-separable state. This one like completely non-separable, like in a extreme meaning. Non-separable or entangled. So this is entangled. state. Entangled states. So this is nothing but the quantum entanglement. You might say that, oh, let's take another another. For example, let's assume that other coefficients like C00 and what else, and C10 equal to 0. Would it be also entangled state? No, because in this case, let's say, but in this case, if we have this superposition 0, 1 plus 1, 1 state, I can represent this as a following product. It will be 0 plus 1 times 0 plus 1 times 1. So I separated this state. So this is separable state and has no entanglement. It's not entangled. Separable state. In contrast to this one, the Bell state is non-separable. And what is more important is that it is correlated, but correlated and non-separable, but in some sense it is like completely non-separable, because I know, like for example, here you still can like calculate, for example, these elements C00 and like even in the classical physics, like in electrodynamics, you can calculate these coefficients and track them to the state of each particular system. In this case, you cannot do so. It is completely, like in some sense, it's completely quantum state, entangled state. Yeah. So do you have any questions about this Bell states, entanglement? Again, we will talk more about entanglement. Here, I just wanted to bring this information in form of the postulate of quantum mechanics, and this is the end of the introduction to quantum theory, with the focus on quantum quantum technology. And next week we will start another next chapter 3, quantum gates. So we will I will introduce the most important quantum gates for, like, so you could you will be able to read quantum circuits. And after that we will talk about some quantum information and teleportation, cryptography, etc., and do some practical works on in programming and simulation of the quantum circuits. So yeah, so that's all for today. Let me stop the recording.
Like this entanglement property can only be seen in the Bell states, means any state in this form. Maybe
No,
that's
this is the
okay.
this is so the Bell state is the like ultimate case of entanglement. Entanglement, you can think about that like a correlation, but this Bell state is kind of the ultimate, the extreme case of quantum correlation. Yeah, let me tell you a little bit more about this. For example, you prepared you have two level systems, right? Like A and B. And you prepare this system in this first Bell state. Without the prefactor, you can write this like this. Right, so just the sum of these two vectors. And then what you do, you can actually split the system, like, and let's set them apart, for example, to a very high distance. You can like say that let's take one part and leave it at Earth and send another one to the moon, and they will be still in this entangled quantum state. And then what you decide to do, you decide to measure your part of your system, your part of this entire system. And for example, if you get on your side, you measure it, you don't know, like, you have to assume that your system is in both, in the superposition of both 0, 0, 1, 1. But then you do the measurement and find your system. You can find your system in either 0 or 1. So you do the measurement and find your system, for example, in state 1. Then you can say that with 100% certainty, with complete certainty, the part of the state that you send to the moon will acquire the state 0. It will be also 0, because if you find 0 here, the another part of the system will be also 0. But if you find your system in state 1, so this is the alternative version of the future, you will say that with 100% certainty, the other state also acquires the state 1. The same way, if you prepare the second Bell state, which is 1, 0, 1 plus 1, 0, right? Then, and you do the same, you prepare the system, split it, and send the second part to the moon. And then you do the measurement. So now, if you detect 0 and at your side, so this is your case, 0 on your side, then you say that your Bell state collapsed to one of these terms, right? To the first one, and the substate B will be exactly in the state 1 with 100% certainty. And vice versa. If you detect 1, you will say that, oh, the state B, substate B, is in the zero state. This is how it works.
Yes.
Yeah, so this is in drastic contrast to the classical physics, like when you have two resonators, you put them together, they share some state, but then you put them apart, and if you measure one resonator, you cannot say anything about the state of the second one. Here you can. So this is the difference. Important one. This is the difference between correlation and entanglement. All right.
Yes.
So let me stop the recording.